Thank you all for coming today. So we've just heard Wooter talk about some of the weaknesses of classical cluster-based inference. Um, so for instance, in a face localizer scan, we might see some clusters, but we can't necessarily say that all the voxels in this cluster are active. We also might be missing some true effects. Also, some of the clusters that we observe here could actually be false positives as well. So there are a number of different ways that we might be interested in quantifying errors that happen in this procedure. So one thing that we might be interested in quantifying, let me just move the caption out of the way. All right, here we go. There we are. So we'd be interested in quantifying how bad this problem is actually in practice. And there are also a number of different alternatives that have been proposed to cluster-based inference. But how can we choose one procedure over the other? How can we tell which is better? So today I'm going to talk about some procedures for comparing and estimating error rates, with the typical goal to increase the number of true positives we detect and decrease the number of false positives. And this is, I'm going to talk about three different sort of typical procedures we could use to estimate errors. So there are theoretical estimation procedures. These can be computationally efficient. So for instance, typical univariate power calculators are sort of like this. We estimate, expected power based on theory. However, we tend to make quite a few assumptions for these procedures. And actually, some of these procedures may not exist for complex inferential procedures that we use in fMRI, for example. So another possibility would be maybe to use some simulation and estimate error rates based on, the known ground truth in these simulations. And this is pretty nice because we can actually control the ground truth, which lets us explore a number of different scenarios. And this also tends to be, fairly computationally efficient compared to what I'm going to talk about next. Not as efficient as a theoretical procedure, but, usually not terribly bad, depending on what sort of size image you're using. However, it may not necessarily be very realistic relative to the actual, complex spatiotemporal structure in the data and whatnot. So a third possibility is to use an empirical estimation procedure where you're actually using real data, and you might be resampling the data or doing other things to the data to estimate error rates. This is nice because it better captures the complex structure in the data that we talked about. However, you can't really control the ground truth, and you still have to make some assumptions about how you're going to use the real data to define ground truth. And you have to think about ways that might be that might actually not reflect reality. But so comparing these three different approaches, the empirical estimation procedure gets you a little bit closer to the truth of the data, and also it lets us estimate error rates for some more complex inferential procedures. So I'm going to talk a bit more about this. Specifically, I'm going to talk about one approach that I've been using and others in the field have been using for a while to empirically estimate errors. So we can start by talking about how we could use this procedure to estimate false positives. So we might start with, all statistical maps, and just note these next few slides will talk about how we can estimate errors in the network context, so functional connectivity. But I just want to note that it's the same procedure for activation maps. So we start with all of the maps across all subjects. And for some number of repetitions, we'll randomly subsample some group of subjects, and then we'll perform a statistical procedure using one inferential procedure. At that point, we'll then aggregate all significant effects, and we can see that anywhere we got a significant effect, we can call this a false positive, because we actually know that the ground truth is null. And so that's an important point, like how we actually generate our ground truth null. So Eklund and colleagues were, I think, one of the first really major examples of this in the field. or at least an example that had sort of widespread implications, where they used resting state data, but then they used task regressors and estimated, task-based activation, but where anything that you found to be significant would be just not necessarily true, because we know that the real data is just resting state and not related to the task. And they use several different types of task regressors, which is also a good potential avenue, because we know that different task regressors can have different effects with null data. And then in the context of functional connectivity, something that we've done is use two different resting state functional connectomes. And we'll contrast one connectome to the next per subject, but we'll actually shuffle which connectome is in the time 1 versus the time 2 slot by subject. So in this way also, we would expect there to be no, temporal structure, everything is at rest. So we expect the null to be true as well. So for benchmarking true positives, we actually use a very similar strategy. We start with all the subject maps, we subsample, we perform some statistical procedure, we aggregate significant results. And for this, we will actually be performing significant results only on one side, because this will help us compare to the ground truth. Because what we're going to do next is we're going to estimate the ground truth using all of the subjects. And we're actually going to use one direction of the ground truth. For example, Cohen's d greater than 0. And we're going to see whether we actually detected effects also in that direction, and how many times we detected effects in that direction. So that lets us quantify both, true positives in that direction, or also positives in the opposite direction of the actual ground truth, and we can call those false positives. So there are a couple ways you can generate ground truth effect maps for this particular scenario. One version used for cluster-based inference, both by Guder and colleagues, with sort of a similar procedure used in a slightly different way by Creamers and colleagues, and also a procedure that we used is to just do, task-based activation to define the ground truth, and then use the subsampling procedure to estimate, true positives from that. And also in the functional connectivity context, we've just used, task-based matrices compared to rest matrices. But as you can imagine, anything that you expect to yield a true effect, you can use as your ground truth. So now that we've talked a little bit about how these algorithms work, we can actually show a couple different practical examples in the context of task-based activation and for functional connectivity. So for task-based activation, as we discussed previously, univariate procedures can be quite conservative in the sense of leading to many false negatives, missing true positives. There are also many variables if you're doing multiple comparison correction, and accumulating evidence has started to suggest that we have quite modest effect sizes, including something I'll be talking about here at OHBM. But cluster-based inference has been proposed as one procedure that can start to address this. It improves power by pooling within the local neighborhood, as we've discussed previously. However, in practice, we actually historically have not been able to quantify exactly how powerful cluster-based inference is. Historically, just like Eklund and colleagues first showed when they were talking about false positive rates, it's been quite difficult to do this. The computational resources were not quite as fast and efficient as they are today, especially for dealing with large imaging data. But now with some of these procedures we just talked about, we can start to quantify this in practice. So let's see what it looks like to benchmark power for task-based activation maps. So here we'll start with, all the subject maps like we discussed before. We can estimate the ground truth effect size across all subjects. And then we can also resample 20 subjects per group and perform one of a couple different inferential procedures. Here, we're using standard cluster-based inference and TFCE, which is proposed to be a improvement over that procedure that I think people will be talking about later. And then we can look at the true positive rate by comparing, the positives we observe across all those repetitions to the ground truth. And I'd also like to note that we're looking at 5 different tasks in the Human Connectome project, which range about 400 to 500 subjects per task. So now let's look at what power we get from task-based activation. So here's a sort of complicated figure that I'm going to break down, and we're just looking at the social task for right now. So in this gold-orange color, we're showing the proportion of voxels that show each effect size. So this is basically just a histogram of effect sizes. And in blue, we're showing power, or you can think of as the true positive rate in terms of percentage. So percentage of time for each individual voxel, we see that we detect that effect and we know that there's a true effect there. So here I'm just highlighting where a medium Cohen's d effect size is, 0.5, both on the negative and positive directions. And we can see that power is about, it's about 20% power to detect an effect at that effect size, which is, much lower than our typically targeted 80% power threshold. And note also that we observe, approximately 1% of voxels show a medium effect size. If we were to just look at, a small area to the right and left of that Cohen's d effect size. But note that, most effect sizes are going to be much, much smaller than that medium effect, since so few effects are, at medium already. And this replicates across a number of different tasks. We see a slight improvement for TFC, rather a notable improvement. And I also want to point out that I've shown the Bonferroni corrected. If you just did a univariate inference and did Bonferroni correction, that's that very lowest curve. And you can see that we definitely have much better power than we would expect from Bonferroni correction, but we still have, quite suboptimal power to detect most effects. And because so few effects are, even medium in size, we should expect much less than 20% power for the majority of effects. So we talked about, empirically benchmarking error rates for task-based activation. Now we're going to talk about empirically benchmarking error rates for functional connectivity. And again, we're sort of more so focusing on power here, since others have looked at the issue of false positives. And everything that I'm showing here, we also use empirical benchmarking to show that we control the false positive rates as expected. Here, we're more so referring to the fMRI's error rate for most cases. All right, so moving on to functional connectivity. So as I mentioned previously, cluster level inference was proposed in the context of activation mapping to improve power by pooling within the local neighborhood. This has also been translated to the context of networks by Zaleski and colleagues. So now we have components instead of clusters, but it's still the same idea. You're grouping together things in a graph component if they're still attached to each other by a node, at least one node, or rather nodes are attached to each other by edges, but you can think of edges attached to each other by nodes above once you apply this threshold. However, there are a few limitations, including some that we've just talked about. First, we see sort of in the activation context that there's this tip of the iceberg style effect, where when we use the full data set, we tend to see these widespread, very structured activations. But when we have smaller data sets, we tend to see only sort of the tip, like a hotspot of this widespread activation. We see some hint of this potentially in the network context, where when we group together edges, we tend to see edges grouping together in these canonical large-scale resting state networks, suggesting that there is also widespread significant structure in that context as well. And then, as we discussed previously, we tend to see quite low power when we're using cluster level inference, probably as a result of the fact that we're only getting the tips of these icebergs. So something that I was wondering was, given our observations of these widespread effects in both the activation and potentially the functional connectivity context, could accounting for widespread dependence actually help us improve power? So I've introduced a couple new inferential procedures to try to account for this dependence. And in the interest of time, I'm going to be glossing over these, but feel free to, reach out with any questions. One is a network level inferential procedure, the constrained network-based statistic. And in brief, what we're doing is we're just pooling within these predefined, we partition the network, and then we pool within these predefined groups that we've partitioned the network into. So here I'm using the Shen Atlas. There's 55 different subnetworks that I'm using for pooling. And this has a couple nice features. One is that there's no contiguity requirement. We can pool across areas that are very widespread, but not actually connected components in the network. And we know that there's some dependence across these widespread areas. And another is that there's no assumption that statistics are identically distributed. So different networks have their own unique nulls that are estimated. And I've also extended this to the whole brain level with the multivariate CNBS. So we just take that 55 different statistics from the CNBS, and we treat it as a single vector, and we use that vector for inference. So this has a couple of nice properties. It combines information across the whole brain, and there is thought to be some dependence at that level. And another nice property is we're only performing a single test. So there's no need to do this multiple testing correction, which increases power. Feel free to check out those references if you'd like to learn more or reach out to me. So here are the results, or rather a really quick overview of how we benchmark and then getting into the results. So it's very much what you've seen before. Here, though, we're using 8 tasks, and we're estimating functional connectomes here, and we're doing task versus rest contrast. And also for fMRI's error rate estimation, we do rest versus rest shuffled, as I discussed previously. Again, all subjects, subsample 500 times, using 3 group sizes here, and 7 inferential procedures that go from the lowest level of inference to the highest at the whole brain, and the lowest being the edge. And we aggregate all significant results and compare to the ground truth from all subjects. And then we compare these two things to estimate true positive rates. So again, this is yet another benchmarking procedure, and this is applied to functional connectomes. Do many different experiments combining all these tasks and group sizes and procedures, but let's look at the actual power that we estimate. So on the left is the lowest level of inference edge, all the way to the right is whole brain. And you can see, as you'd expect, as we get to these wider scale inferential procedures, we actually improve power quite substantially. And this holds, as we increase sample size, as you'd expect. But something I'd like to highlight is that only the more global approaches, the network level and whole brain approaches, get us to adequate 80% power, that commonly targeted threshold on average, whereas the other procedures are sort of below that typically targeted threshold. And I also wanted to point out that there's a pretty significant advantage for FDR control, such that edge level FDR correction, we tend to see better power than the cluster level approaches. And this is something that's pretty well known, that FDR will allow us to get better power than fMRI's error rate correction. But I think it's useful to see this empirically, the advantage for FDR is being so strong that we can see an edge level procedure outperforming the cluster level procedure. And that's what I think is a really nice advantage to using empirical benchmarking to show the practical gains that we can expect to see for our procedures. So really quickly, I just want to highlight that there's a number of other empirical benchmarking types of studies that have been done in the past decade or so. I'm highlighting a couple big ones that I think have been pretty impactful, but there are actually many others as well. Eklund and colleagues showing that we might not control false positive rates, fMRI's error rate specifically, as expected with parametric procedures. American colleagues showing that we may not have as great reproducibility as we might otherwise hope to have. And then a recent variation on that by Makowski and colleagues showing that using multivariate procedures, we may actually get better reproducibility. There are a number of critical considerations when we're using empirical benchmarking. I think the chief amongst these is to really carefully consider how believable your ground truth is. Are effects due to the contrast or inference of interest? Maybe they're due to confounds. It's worth considering that. You're also still with the full data set, there's still sampling variability, so there are errors there. If you're using null-based procedure, if you're interested in simulating a null, does your null actually behave like a null? And I think that there are similar implications across other multidimensional data types. It's worth considering, if you're looking at multivariate approaches, the meaningfulness of the scale can be hard to compare multivariate errors to univariate errors. But it's nice that we can leverage larger than ever data sets to inform our benchmarking and future inference. So a quick summary is that we can use these resampling-based empirical error benchmarking approaches that match the complexity of the data and also allow us to evaluate more complex procedures. There's a major caveat, which is we still have to understand the realisticness of the ground truth. And very much in the spirit of beyond blobology, we actually see that traditional cluster-based procedures tend to be much less powerful than typically targeted for many smaller sample studies. We get better power with broader scale and multivariate approaches, but of course, sacrificing some spatial specificity. So at this point, I'd like to say thank you all for listening, and thank you to many people who have contributed to different elements of this work over the many years. Thanks.